Category O, Lecture 15, S-subcategories in O. Let us start with recalling the notion of the Serre quotient of an abelian category. Let A be an abelian category. A full subcategory C of A is called a Serre subcategory, provided that for any short exact sequences, when X is a submodule of Y with the corresponding quotient Z, we have that the middle term Y belongs to the subcategory C if and only if the terms X and Z belong to C. For example, the full subcategory given by the set of objects which ascend to 0 by a fixed exact functor is always a Serre subcategory. Given a Serre subcategory C of an abelian category A, we can define the quotient A divided by C as the category which has the same objects as A and such that for X and Y in A, the home space from X to Y in the quotient A modulo C is defined as a direct limit of the homes from X prime to Y divided by Y prime, where X prime is a submodule in X such that the quotient belongs to C, and Y prime is a submodule in Y such that Y prime belongs to C. And the classical property is that this quotient is an abelian category. And the canonical functor, the canonical projection functor phi from A to A divided by C is exact. Let us now talk about centralizer subalgebras. Consider a finite-dimensional associative algebra A over a field K. Let E be an idempotent in A. The algebra EAE, which is isomorphic to the opposite of the endomorphism algebra of the projective A module AE, is called the centralizer subalgebra of A associated to the idempotent E. We have the exact functor, which we denote by Fe, which is given by taking homomorphisms as A modules from the projective module AE to blank. So this is a functor from the category of all A modules to the category of all EAE modules. This is because the projective module AE has the natural structure of an A EAE bimodule. Note that for any A module M, we have that the image of M under the functor Fe is 0 if and only if E times M is 0. Let us denote by Xe the full subcategory of A mod consisting of all modules which have a two-step presentation by projectives in the additive closure of the module AE. And it is very easy to check that the functor Fe provides an equivalence between the category Xe and the category of modules over EAE. So now we can combine these two notions. First of all, we know that Serre subcategories of A mod are in bijection with subsets in the set of the isoclasses of all simple A modules. Indeed, if C is a Serre subcategory in A and M is an object in C, then M has a finite composition series, and therefore, because of the condition for the Serre subcategory, it follows that all simple subquotients of M are in C. Conversely, given a set of simple modules in C, any A module M which has only these simples as composition subquotients belongs to C, again because of the condition on the Serre subcategory. Therefore, each Serre subcategory of the category of finite-dimensional A modules is uniquely determined by the simples which this category contains. Moreover, it consists of all objects whose all simple subquotients are these simples. Corollary, let C be a Serre subcategory in A mod, and E be an idempotent in A such that the projective module AE is an additive generator in the category of all A projectives whose stops lie outside C. Then the quotient A mod divided by C is equivalent to the category of modules over EAE via the functor Fe. Proof. First we note that the functor Fe kills the category C. This follows directly from the assumptions because we have assumed that the top of the projective module AE consists of simples which lie outside C. Furthermore, for two modules X and Y in the category XE, we have that the home from X to Y in the quotient category is actually equal to the home from X to Y in the category A mod. So this follows by noting that the only choice for X prime in the definition of the home in the Serre quotient is actually X, because the top of X lies outside C. And further, by noting that home from X to any choice of Y prime in Y is 0. This is because the top of X is outside C, while any simple subquotient of Y prime is in C. So therefore this home is 0, which implies immediately that home from X to Y in the quotient is equal to home from X to Y in A mod. Now the claim follows directly from the equivalence mentioned on the previous slide. Let us now talk about recallment of abelian categories. Denote by YE the full subcategory of A mod, which consists of all modules which are killed by the exact functor Fe. It is very easy to see directly from the definition that YE is equivalent to the category of modules over the quotient algebra A divided by AEA. So modules in YE should be killed by the idempotent E. So they should be actually modules over this quotient algebra. In this situation, we have the following diagram. So we have the category YE, which is a subcategory of A mod, and we have the exact inclusion functor, which we can represent as tensoring over A divided by AEA, with the bimodule A divided by AEA, where the right action is given by the quotient algebra and the left action is the action of A. Similarly, we have the exact functor Fe from A mod to EAE mod. This we have already discussed. This functor is given by taking home over A from AE to blank. Both functors are exact, and therefore they have both left and right adjoints. So in this diagram, the upper arrows going to the left are exactly the left adjoints of the right arrows, and the lower arrows going to the right are exactly the right adjoints of the right arrows. And this diagram is called the Recollement diagram for these abelian categories. Let us now return back to category O and recall the classification of projective functors due to Bernstein and Gelfand. Let G be a semisimple finite-dimensional complex Lie algebra with a fixed triangular decomposition. Let lambda and mu be two integral and dominant weights. Let W be the Weil group of G, and W upper lambda the dot stabilizer of lambda. Let O lambda be the indecomposable block of O, which contains the simple highest weight module L lambda. Finally, let P lambda mu be the category of projective functors with domain O lambda and target O mu. Here O mu is of course the indecomposable block of O containing L mu. Then Bernstein-Gelfand's classification says that there is a bijection between the set of isomorphism classes of indecomposable projective functors from O lambda to O mu and the set of W lambda antidominant weights in the dot orbit of the weight mu. So this bijection is given by sending a functor zeta to the indecomposable projective p nu indexed by such w lambda antidominant weight in the w dot orbit of mu, and the weight p nu is understood as the image of the dominant projective module p lambda under the functor zeta. We have already defined S-subcategories in O in relation to Bernstein-Gelfand classification of projective functors. Let P be a parabolic subalgebra of G containing the Borel subalgebra H plus N plus. Denoted by WP, the parabolic subgroup of W generated by all simple reflections, which corresponds to negative simple roots occurring for the Levy factor of P. Denoted by X of WP, the set of all WP antidominant weights with respect to the dot action. Recall that a projective module is called WP admissible if all its summands are isomorphic to P of mu, where mu belongs to X of WP. So all summands should correspond to WP antidominant weights with respect to the dot action. Then we have defined the category SWP as the full subcategory of O consisting of all modules which have a presentation, a two-step presentation by WP admissible projectives. If we denote by IP the Serre subcategory of O generated by all simple highest weight modules L mu, where mu is not a WP antidominant weight with respect to the dot action, then from the discussion above, we can realize the S subcategory S of WP as the Serre quotient of the category O by the Serre subcategory IP. And of course, from this realization, we see that the only simple modules which survive in the S subcategory are those which are indexed by the WP antidominant weights with respect to the dot action. So this means that such weights are actually indexed by the double cosets of W, where on the right we have the action of the dot stabilizer of the dominant weight, the singularity of the block, and on the left we have the action of our parabolic subgroup WP. Consider an SL3, SL2 example. Let G be the real algebra SL3 with a Dynkin diagram given by the following picture. So here S and T are two simple reflections and they are connected by one edge. Let P be the parabolic subalgebra of SL3 consisting of these kind of matrices where this negative simple root corresponds to the simple reflection S. Then the Weil group of G is the symmetric group S3 and it has the following elements E, S, T, ST, TS and W0, which is STS and TST. The parabolic subgroup WP consists of the elements E and S. Let H in W be a parabolic subgroup which describes the singularity of our block. Then, depending on the choice of H, we have the following weights which give us elements in the S subcategory S of WP. So if H is trivial, then we have the regular block with 6 weights indexed by the elements in W, and the longest elements in the left WP cosets are the weights S, ST, and W0. If H is E and S, then we have 3 cosets, ES, TS and T, and W0 ST. So we have 3 cosets modulo H, and these give rise to 2 double cosets with the longest elements ES and W0 ST. So if H is the subgroup consisting of E and T, we have 3 H cosets, ET, SST, W0 and TS, and again these give rise to two double cosets with the longest elements represented by S and ST and by the coset W0 and TS. Finally, if H is the whole of W, we have one H coset, which is just the W, and it is also the double coset and the longest element. So we have one element in the corresponding block of the S subcategory S of WP. Now I want to discuss an alternative motivation for the study of S subcategories in O. Consider the Levy decomposition of P, so it's a sum of the Levy subalgebra L and the nilpotent radical N. We can further decompose the Levy subalgebra L as a sum of the semi-simple part A and the center, which we denote by HA orthogonal. So this is an abelian subalgebra, the center of L. Given an A module V and a weight mu in the dual space to HA orthogonal, we can extend V to an L module by defining that elements H in HA orthogonal act on elements in V as scalars prescribed by the weight mu. So H dot V is equal to mu of H times V. Further, we can set that V is killed by the nilpotent radical N, and this turns then V into a P module. Then we can consider the usual tensor induction. So starting from V, we tensor over UP with U of G to get a G module out of the module V. So the corresponding induced module is denoted by M of V mu, and one usually says that M of V mu is obtained from V and mu by parabolic induction. So for example, we can view Verma modules as obtained by parabolic inductions from the degenerate case, where P is the Borel subalgebra B, V is a one-dimensional module, and lambda is an element in H star. More generally, we can define G modules which are called generalized Verma modules. So if we take any weight nu in the dual space to HA orthogonal, then the construction on the previous slide defines a parabolic induction functor psi nu from A mod to G mod. Note that this parabolic induction is exact by the Poincaré-Birkhoff-Witt theorem. For any simple A module L, the corresponding parabolically induced module ML nu is called the Generalized Verma module, or GVM for short, corresponding to L and nu. Please note that there are no restrictions on the module L apart from the fact that it is supposed to be simple. So it might be finite or infinite dimensional, it can be a weight module or a non-weight module, no other restrictions. We also denote by HA the intersection of the Cartan subalgebra H of G with the semi-simple algebra A. So for example, if lambda is a weight over H, we can consider mu the restriction of lambda to HA and nu the restriction of lambda to HA orthogonal complement. Then, from the associativity of the induction, we can view the Verma module delta lambda as being parabolically induced from the Verma module delta A of mu, so the Verma module with weight mu over the algebra A, and then the parabolic induction is given by the weight nu. In the case where the Verma module delta A mu is simple, we get that delta lambda is also a generalized Verma module. Another easy example of generalized Verma modules are actually parabolic Verma modules. So they are induced from simple finite dimensional modules over the parabolic subalgebra. So the original motivation for study S subcategories in O comes from the question to describe the structure of generalized Verma modules. This is still an open problem in the very general case. There are some partial results. In particular, there is an irreducibility criterion which is known in the case where the semisimple algebra A is a semisimple part of the parabolic subalgebra is of type A. So this can be found in my paper with Katarina, which is called Categorification of Induced Cell Modules and the Rough Structure of Generalized Verma Modules. So the basic idea behind the approach, how to study the structure of generalized Verma modules, is due to Serre and can be explained as follows. We can try to embed a generalized Verma module into an appropriate generalization of category O, on which there is an action of projective functors. Using the action of projective functors, we might get an equivalence between this category and a certain category of Harish-Chandra modules. Using the Bernstein-Gelfand equivalence, this will give rise to an equivalence between our category and a certain subcategory of category O. And then we can read off the result using the Kazhdan-Lusztig combinatorics of category O. So in the case when the annihilator of the simple module, which we use to produce the generalized Verma module, in the case when this annihilator is a minimal primitive ideal, then the corresponding category to which we need to embed the corresponding generalized Verma module is usually equivalent to a block of some S subcategory in O. So this explains the relevance of S subcategories in O in the structure of Verma modules. So let us now talk about standard and proper standard objects in S subcategories in O. Fix a weight nu for the Lie algebra HA orthogonal complement. Let mu be an HA weight which is antidominant with respect to the dot action of WP. Then we have the canonical quotient functor from O to the S subcategory S of WP. So we define the standard module delta mu nu as the image under this quotient functor phi of the module which is nu parabolically induced from the projective injective module PA of mu over A. So this is a projective module, but since mu was antidominant, it is also injective. And we define the proper standard module delta overline mu nu as the image under phi of the module which is nu parabolically induced from the simple module LA of mu. Alternatively, we can consider the module L hat A of mu, which is defined as the quotient of PA of mu by the trace of PA of mu in the radical of the PA of mu. And the claim is that the module delta overline mu nu is equal to the image under phi of the module which is nu parabolically induced from this L hat A mu. And the reason for that is that the natural projection from LA hat mu to LA mu by construction has the kernel which doesn't contain any WP antidominant subquotients. So when we parabolically induce this kernel, we will not have any WP antidominant subquotients either, because parabolic induction is essentially applying projective functors, and applying projective functors we cannot get antidominant simples from non-antidominant simples. And therefore, when we apply the quotient functor phi, which only sees antidominant simples, we will get that this functors annihilates psi nu applied to the kernel. And therefore, the two realizations of the module delta overline will coincide. So now we can describe the properly stratified structure of the S subcategory in O. A consequence from the discussion on the previous slide is that if mu is not an antidominant weight, then phi kills the module which is parabolically induced from LA mu. Next, let us note that the standard module delta mu nu has a filtration with subquotients delta overlined mu nu. To see this, we can take any filtration of the projective-injective module such that each subquotient of this filtration has LA mu with multiplicity exactly 1. And now applying to this filtration the exact functor given first by the parabolic induction psi nu and then by the quotient phi, we get the claim of the proposition. Next, we claim that each WP admissible projective module P lambda has a standard filtration. That is a filtration with subquotients being standard modules. So here is a sketch of the proof. First, consider the case where lambda is equal to W0P dot lambda tilde, where lambda tilde is a dominant weight. So in this case, directly from our construction, we have that P of lambda is the delta, where the first parameter is a restriction of lambda to HA, and the second parameter is a restriction of lambda to HA orthogonal. And then the general case can be obtained from this special case using projective functors. So here we use that both admissible projective modules and standard modules are sums of projective-injective A modules, possibly infinite sums. Then cokernels of inclusions of projective-injective modules are projective-injective. That standard modules are free over sigma of n, so here n is an important part of our parabolic subalgebra, and sigma is an anti-involution of G, which maps positive roots to negative roots. And that projective functors preserve both projective-injective modules and sigma n free modules. And then we just follow the usual proof of the fact that projectives in category O have Verma flag, adjusting it to this situation, and the same arguments work. So in particular, we have the following corollary, which is due to Futorne, Koenig, and myself from 2000, which claims that each block of the S-subcategory in O is the module category over a properly stratified algebra. So in particular, we have various properties which are true for any properly stratified algebras. One of them is a BGG reciprocity. So first of all, we know that the simple preserving duality on O restricts to a simple preserving duality on any S subcategory. Indeed, the simple preserving duality has an interpretation as an existence of a certain anti-automorphism of the underlying algebra of O. And this anti-automorphism is supposed to fix some set of primitive idempotents. So we can take this anti-automorphism and restrict it to any centralizer subalgebra. The restriction is well defined because the primitive idempotents are fixed. And this gives us an anti-automorphism on the centralizer subalgebra, which means exactly the existence of a simple preserving duality on the module category of this centralizer subalgebra. And then we have the usual BGG reciprocity. So if we have two WP antidominant weights lambda and mu, then if we take the corresponding projective object, so this is the image under phi of P lambda, it has a standard filtration, and the multiplicity of the standard object corresponding to mu, so this object in our notation had the form delta, then mu restricted to HA, and the second parameter mu restricted to HA orthogonal. So this multiplicity of such delta appearing in the standard filtration of such projective is equal to the composition multiplicity of the L lambda simple appearing in the composition series of the proper standard module delta overlined corresponding to the parameter mu. And again, the reciprocity follows using usual arguments and the fact that the standard and proper costandard modules form homologically dual families. That is, the category of modules with standard filtration is exactly the left orthogonal complement to the category of modules with proper costandard filtration, and the category of modules with proper costandard filtration is the right homologically orthogonal complement to the category of modules with standard filtration. From this, we can easily read off the Cartan matrix of the S subcategory in O, but it also can be read off directly from the definitions. For any WP antidominant weights lambda and mu, the multiplicity of the mu simple in the lambda projective coincides with the multiplicity of L mu in the projective module P lambda. So here we speak about the usual multiplicities in category O. So this follows directly from the definition. So this is given by some home between some projectives and the quotient functor is full and faithful. So here is an SL3, SL2 example again. Consider the regular block, then the indices for the S subcategory corresponding to the simple root S in the regular block are exactly S, ST, and W0. Here we have the graded filtrations of the proper standard, and projective modules in the regular block of this S subcategory. So the proper standard module corresponding to W0 is simple. The proper standard module corresponding to ST has lengths 2, with W0 in the socle and ST on top. And the proper standard module corresponding to S has W0 in the socle, ST in the middle, and S in the top. The standard module corresponding to W0 has delta over line W0 twice. Notice that they are in the degrees 0 and 2. All the structure is inherited from category O. So delta ST has this graded filtration and delta S has such a graded filtration. So we just take the corresponding delta from category O and apply the quotient functor, which means we forget certain simples. This is what is left. And here is the description of PW0. Maybe we should start from PS. So the module PS coincides with delta S, so it's the same as delta S. Then PST has delta S once and then delta ST. So the multiplicities are 1. So the multiplicity of delta S in PST is equal to the multiplicity of LST in delta over line S, which is 1. And then PW0 has each standard module once, because W0 appears once in each proper standard module. So we will get this module. And here's a picture for the singular block with singularity ES, and also with the S subcategory given by the same ES. So we have indices S and W. So graded filtrations of proper standard and projective modules are given here. So now we have two simple modules. The proper standard module for W0 is simple, and the proper standard module for S has S in degree 0, this is the top, and W0 in degree 2. So TS is a gray simple which exists in category O, but it disappears in the S subcategory. So delta W0, so this is how it looks in category O, and TS is gray, which means that it disappears in the S subcategory. And delta S, this is how it looks in category O, and again TS is a gray simple, it disappears in S subcategory. And then the corresponding indecomposable projectives, so PS is the same as delta S, and PW0 has delta S once, and delta W0 also once, because here we have multiplicities 1 and 1 of W0 in the proper standard modules. So similarly to category O, S subcategory in O has an analog of Serre's combinatorial description. So indecomposable projective objects in the S subcategory in O, by construction, they are exactly the indecomposable WP admissible projectives. That is, they are of the form, the image under the quotient functor phi of P mu, where mu is WP antidominant weight. Please also note that all projective injective modules in O are WP admissible because they are globally antidominant. In particular, they are WP antidominant. So we have the following Serre's combinatorial description from the same paper of Torniker and myself. So each indecomposable block of SWP contains a unique indecomposable projective injective module. The endomorphism algebra of this indecomposable projective injective module is the same as in category O. So in particular, it's either the coinvariant algebra on the nose or the algebra of certain invariants in the coinvariant algebra. Taking homomorphisms from this indecomposable projective-injective module gives a functor which is full and faithful on all other projective modules in this block. And this follows quite directly from Zergil's combinatorial description in category O. We just apply the functor phi, which is full and faithful on all WP admissible projectives. And we get all those claims. So we reduce them to the corresponding claims in O. We also have, similarly to category O, the property of dominant dimension of the block. So each indecomposable block of the S subcategory in O has dominant dimension at least 2 with respect to the projective-injective module in this block. In other words, any projective module in the block admits a 2-step co-resolution by projective-injective modules. Proof. Consider the dominant standard module in the block. The preimage of this dominant standard module in category O has a Verma flag, and the socle of any Verma module is a simple Verma module, which in turn is the socle of the indecomposable projective-injective module. Therefore, the home space from the indecomposable projective-injective module to our dominant standard module, and in particular to our proper standard module, is non-zero. By the BGG reciprocity, it means that our dominant standard module is a submodule of the projective-injective module, and the corresponding cokernel has a standard filtration. In particular, the cokernel must have a projective-injective envelope. So this means that our dominant standard module has a 2-step co-resolution by projective-injective modules as claimed. Now we can apply to this dominant standard module all possible projective functors and get similar co-resolutions for all other projective objects. Also, similarly to category O, we can describe tilting modules in S subcategories. The claim is that the indecomposable tilting module in the S subcategory S of WP, so each indecomposable tilting module is also cotilting, and it actually has a form, the image under phi, of the tilting module T of gamma, where gamma is a WP dominant weight. Proof. Consider the anti-dominant standard object delta mu. Since it's anti-dominant and standard, it must be tilting. So this object is the image under phi of the module which is nu parabolically induced from some projective-injective module in the category O for the algebra A. But since the projective-injective module has simple socle, and this socle is not killed by the quotient functor, it follows that the standard module delta mu nu has simple socle. In particular, this means that the standard module also coincides with the corresponding co-standard module, and hence is both tilting and cotilting. Now, applying projective functors, we get that all tilting modules are direct summands of the images under projective functors of a module which is both tilting and cotilting, and hence they all are both tilting and cotilting. Also, if we know that the projective-injective module is exactly a tilting module, now it's projective-injective for the anti-dominant weight, but it is tilting for the dominant weight. Therefore, it follows that our original anti-dominant standard module was the image under the functor phi of a module which is parabolically induced from a dominant tilting module. So in particular, the module which is parabolically induced from a dominant tilting module at the anti-dominant level, this module is itself a tilting module. So in particular, this anti-dominant standard module is the image under phi of a tilting module whose weight is WP dominant. Applying projective functors, we get exactly that all tilting modules should have this kind of form, as claimed in the theorem. So here is again an SL3, SL2 example. If we look in the regular block, we have 3 weights, S, ST, and W0. Here are the graded filtrations of the proper costandard, standard, and tilting modules. Again, we take the corresponding objects in category O and look at what survives when we apply the functor phi. So the proper standard module for W0 is simple. For ST, it has W0 on top and ST in the socle. And for S, it has W0 on top, ST in the middle, and S in the socle. The standard modules we have already seen. And now the tilting modules. So we have the antidominant standard is tilting. And then we have antidominant standard on top of the next standard. This gives us the tilting module TST. And the projective injective module is, of course, the tilting module for the dominant weight. We have a similar picture in the singular block with the singularity given by the same parabolic subgroup as the S-subcategory parabolic subgroup. So we have two weights, S and W0. And here are the graded filtrations of proper standard, standard, and projective modules. Again, so the antidominant proper standard is simple. The next proper standard has two subquotients, W0 on top, S and S in the socle. So TS is a great module, so this is a connecting part in category O. Deltas we have already seen, and the antidominant tilting is the same as delta. And of course, the dominant tilting is just the projective injective module, appropriately shifted. In the setup of S subcategories in O, we also have Ringel self-duality. So the claim is that the regular block of the S subcategory in O is Ringel self-dual. Proof: let P prime be the parabolic subalgebra of G, which is obtained from P using the symmetry of the linking diagram corresponding to the conjugation by W0. Clearly, because we are just talking about something obtained by a symmetry of the linking diagram, the corresponding S subcategories in O are equivalent. The dominant projective in the trivial block for the S subcategories corresponding to P is the image under the functor phi of the indecomposable projective PW0P. And this projective is obtained from delta E by applying the indecomposable projective functor theta W0P. Note that W0P multiplied with W0 is equal to W0 multiplied by W0P prime. So this is a definition. P prime is obtained from P using conjugation by W0. The standard tilting module in the trivial block of the S subcategory of O corresponding to P prime is similarly obtained at the imager under phi of the theta W0P translation of the antidominant Verma module, which is the antidominant simple. Of course, we have that theta W0P applied to delta W0 is a submodule of the theta W0P applied to delta E, and that this submodule is actually the trace of the projective injective module in the projective module PW0P. So it follows that in decomposable tilting modules in SW0P prime 0, in the trivial block of the S subcategory corresponding to P prime, coincide with the trace of the antidominant projective module in the indecomposable projective module in the trivial block of the S subcategory corresponding to P. Applying the double centralizer and the dominant dimension argument similarly to category O, we get that the restriction to this trace provides a Ringel self-duality between the trivial blocks for S subcategories of P and P prime. And this implies the statement of the theorem. Here is again an SL3, SL2 example. So in the regular block we have the indices S and ST and W0. And the trace of projective injective modules in projective modules are as follows. So for the antidominant projective, it's of course projective injective, it coincides with itself. For PST, so the trace is here given in violet, here is this part. And for PS, the trace is again given in violet. So it contains of W0, ST, and W0. And the point is that this trace is not a tilting module for the same S-subcategory in O, because the tilting module, which corresponds to the antidominant weight W0, is as follows. There is no ST in the middle. So this ST in the middle somehow says that this is a different module. It's not the tilting module, but it's a different module, and this is a module which connects this S-subcategory in O to the S-subcategory in O corresponding to the algebra P prime. Some questions for PhD students. Prove with all details that the functor Fe induces an equivalence between the category Xe and the category of all finite-dimensional EAE modules. Question number 2. Prove with all details that the category YE is equivalent to the category of all finite-dimensional modules over the quotient algebra A divided by AEA. Question 3. Prove that the parabolic induction functor psi nu maps category O for the Lie algebra A to category O for the Lie algebra G. Question number 4. Prove with all details that all WP admissible projectives have a standard filtration in SWP. And question number 5. What happens with Ringel duality for singular blocks of the S subcategory in O? Thank you and see you next time.